We've come to the end of my video series on Chapter 4, Open Systems. And you have covered a lot of ground. You've worked on a lot of homework problems. And let's recap to see where you've been and see if we can simplify what you have in your head to try to keep things straight for the types of problems that occur most frequently. And then let's look a little bit ahead of where you're headed next. It's been one of my goals in these video series to try to help you keep it as simple as possible. In Chapter 4, Open Systems, we started with some pretty complex things. And so remember, I marked them down as hard and easy, and it started out pretty hard. I think we started with the continuity equation that was pretty easy to understand, but then we got into a general statement of the first law of thermodynamics. Very confusing, very difficult to really keep track or keep straight. What's this all about? And then we started making some simplifications for frequently occurring problems. Okay. And the objective is to try to go from hard to easy. Now, you may not ever reach that easy goal, but I do want to suggest that if you can keep things simple in your head, it will be less and less hard. I recall that, so I went into graduate school and focused on thermal and fluid systems courses because I found them to be the hardest and most challenging. And I found a number of the other types of courses in mechanical engineering to be kind of easy. So I wanted to take on the thermal systems type courses because I found them to be challenging. And also I was inspired by my dad, who was a worked in a lot of thermal systems throughout his career. And so that's another reason that I went into graduate school and focused on thermal fluids type topics. So let's get started to see if you can start simplifying or try your best to keep these fundamentals simple in your head. Well, we're going to start out tough. Any open system. So remember, here was our sketch, and man, it was a pretty involved sketch, wasn't it? Because we've got lots of mass flows in, lots of mass flows out. We call the in I, the out E. We've got heat transfer rate coming in, output power coming out, and we made it generic. So things could be changing all over time. At 8 a.m. is different than 9 a.m., and that's different than 10 a.m., and on and on and on. So the rate of things is changing all through time. And so we derived the continuity equation. Okay, the continuity equation, conservation of mass, and you thought, okay, well, this kind of makes sense. If we step through it, we've got dm dt of the control volume, the rate at which the mass of the control volume changes. Is it getting fatter or skinnier? Okay, and that's simply made up of if you sum up all the mass flows in, getting fatter, okay, and subtract off all the mass flows leaving, getting skinnier, that's an expression of the rate at which the mass of the control volume changes. And you say, okay, I think I can live with that. We didn't have any specific homework problems exactly with that, maybe a little bit, but not a whole lot. And then we got even more complex. We said, now we're going to do an energy balance. We're going to derive the first law of thermodynamics from fundamentals. And so let's see what was involved in that. So I tried to convince you that the easiest way to visualize the first law is to put the boundary phenomena on the left. So we've got Q dot in minus W dot out. So those are the two boundary phenomena equals a number of terms, sort of three blocks of terms, dE dt of the control volume. In other words, the rate at which the energy of that cloud control volume is gaining or losing energy. And in my world, I think about, kind of getting fatter or skinnier, okay, in terms of energy. Plus another term, if you sum up all the m dot leavings times enthalpy terms, HE, kinetic energy, potential energy, those would be kind of like an energy transport term leaving. minus another big old block of terms, the sum of the m dot n with those related enthalpy terms there. Okay. And let's see, how did H come into play all of a sudden in chapter 4? It had to do with flow work. Now, so we went through it, we remembered it, but we just got exposed to that. That didn't come into problem solving other than remembering that when you have open system problems, you're dealing with enthalpy, not internal energy. All right, enough of this general stuff. We looked at it and we studied it and we said, how can we simplify for real problems that occur more frequently than this general problem? So we stayed with the same sketch, but we said, okay, what about when things are not changing in time? When things aren't changing in time, this cloud is not getting bigger or littler. Can we write down the continuity equation and can we write down the first law of thermodynamics? And the answer was yes, absolutely. We're eager to simplify. So we've got exactly the same sketch, but the continuity equation becomes really easy to understand, common sense. The sum of the mass flows coming in, if you add them all up, they've got to exactly equal the sum of all the mass flows out when you add them all up. It's a little bit like an accounting problem. That statement of steady state, steady flow, continuity. We said, well, let's work on that same thing for the first law. All right, fine. The left-hand side is going to be the same. Q dot in minus W dot out equals. Well, we dropped out an energy rate change term, dEdt, that dissolved, okay? And then we realized, okay, now we've just got two terms that we can remember. We've got m dot leave, the sum of all the m dot leaving, enthalpy leaving, and those other terms, okay, minus the sum of the m dot in, Hn, and other terms. And we remember in our minds how to group those other terms together. And so, wow, so the only thing to remember there is which comes first, I or E, in or out. And my suggestion is if you've solved enough homework problems, if you've gotten enough practice, you'll be able, you remember that it's m dot leaving, H leaving, minus m dot in, H in. That's the way you remember that, is through practice and experience, okay? If you don't have a formula sheet, it's through your practice and experience that you remember this. Okay, and so that helps for multi-inlets and multi-outlet, open system, steady state, steady flow control volumes. We can solve some engineering problems with this. That's great. But then we observed that in a lot of cases, there's an awful lot of engineering equipment out there, manufacturing equipment, processing equipment, and they're not exactly clouds. They're other things, but typically they have only one inlet and one outlet. So instead of a cloud, it might have something like a turbine or a compressor or a pump, and so or a nozzle. And in my sketch, for talking here, I've labeled my outlet state E and my inlet state I. So instead of 1 and 2, it helps me keep straight about I and E, in and exit, instead of 1 and 2. Okay, so well, what's the statement of continuity? For this situation, steady state, steady flow, one inlet, one outlet, m dot exiting equals m dot in. Common sense. And then we said, we're just going to call that m dot. Since they're both equal, we'll just call that m dot. Okay, great. And that helped us simplify even the first law of thermodynamics for an open system, steady state, steady flow with one inlet, one outlet. I find it pretty easy to remember. This was my job, so of course I found it easy to remember. Q dot in minus W dot out, same old thing on the left-hand side, equals m dot, the mass flow rate, times basically three terms. Enthalpy change term, out minus in. Kinetic energy change term, out minus in. Potential energy change term, out minus in. So I found that even at the undergraduate level, pretty easy to remember. So after working through a number of homework problems and getting that experience for writing 2 and 1 or E and I had this thing nailed. It is my hope that you have this nailed in your head so that you don't have to waste time in a time situation, go into a formula sheet or fishing through notes or however you're allowed to do, don't waste time on that. Have this in your head, because by and away, the most frequently occurring problem is going to be, for an open system, will be steady state, steady flow, one inlet, one outlet. Hope that helps you simplify things in your mind. Now, then we went off and we looked at a special case. Your book calls it a transient flow, a transient process. I call it uniform state, uniform flow. And it's a rather complex sketch, isn't it? I started with a piston and cylinder, but it's not a closed system because I've shown a bunch of things flowing in and a bunch of things flowing out through some process 1 to 2. Okay. I've shown Q in and W out, the traditional heat added and W out. No dots on this because we're looking at process state, going from state 1 to state 2. So there's no dots there. Okay. And so let's see, what was a statement of continuity? You can kind of figure it out with common sense. The final mass, M2, well, we know it's going to be at least the initial mass, and it's going to be more based on how much mass you add, the sum of the m dot n's. And it's going to be less based on the sum of the masses that you take away, m dot leaving. So it's kind of common sense 101. M2 equals M1 plus the sum of the m ins minus the sum of the m outs. The first law, it was tougher. This is not common sense 101 whatsoever. We went back to the general statement of the first law. We kind of derived this final relationship, and I'm going to openly admit, right, that even at my advanced age, I do not have this one in my head. I've got to go back to my notes to get this one straight. But let's look at what's in it anyway. Left-hand side, look at a similarity. Q in minus W out equals. Now, the first two terms I've got nailed. M2 U2 minus M1 U1. That's simply capital U2 minus capital U1. That's capital U2, the ending in internal energy minus the beginning internal energy. I got that. But then the trailing terms, I'm going to have to tell you that I have to refresh my memory frequently on. It's plus the sum of the m dot leaving H leaving minus the sum of the m dot in H in. Now, to try to get this in my head, if I totally don't have my notes and I'm a little discombobulated, I remind myself the similarity to the steady state, steady flow open system model to get my E's and my I's straight. But I'm going to openly tell you that I typically have to go back to my notes to refresh my memory on uniform state, uniform flow, first law. So here we are. Let's recap. And the title of my recap slide is, what's the formula? X. Well, I hope I'm trying to convince you that if you come to depend on a formula sheet, a lot of specialized formulas applying to this and that and the other thing, that's going to be a losing proposition. It's going to hurt you in terms of time management and hurt you in terms of really fully understanding the fundamentals of thermodynamics. So chapter 4, we look totally at open systems only. In chapter 4, we focused only on the continuity equation, conservation of mass, and the first law of thermodynamics, conservation of energy. And it is my hope that you can maximize what you get into your head. Try to learn these tricks for keeping it simple, because what's coming up in chapter 5, I would suggest, is a little harder than chapter 4. There are some things that didn't fit in my common sense 101 toolbox. So chapter 5 can be some concepts that are a little tough to understand, but that's where we're headed. So best of luck on any upcoming tests that you might be having. And we're going to prepare then to undertake chapter 5 now that we've completed chapter 4. I hope that helps. It's really been a pleasure preparing this material outside of the classroom environment, because I have prepared in terms of clock time, there's more video time spent than I spent teaching these fundamentals in the classroom. And so I hope you find these videos useful, and I hope you can pull out at least a few tricks on how to keep things simple in your head so you can focus on getting the fundamentals in your head and becoming a better and better engineering problem solver.